What if I told you that the biggest water reservoir on our planet isn't the Pacific or the Atlantic or any ocean you've ever seen on a map? What if it's hidden, locked away hundreds and hundreds of kilometers right under our feet? Well, let's dive into this incredible story, because it's all about geology, chemistry, and the hidden ocean of truly staggering proportions. And I'm not kidding when I say staggering. This deep Earth reservoir isn't just big, it's colossal. Scientists now estimate it could hold up to 3 times more water than all of the world's surface oceans combined. Yeah, you heard that right. Take all the water you know, times 3, and it's trapped deep inside the planet.
So the first thing you're probably picturing is this massive underground sea, right? Like something out of a Jules Verne novel, a vast, liquid world just waiting down there to be discovered.
But that's where this gets even weirder and way more fascinating. Nope, it's not a liquid ocean, it's not ice, it's not vapor. This water exists in a kind of fourth state. It's been chemically taken apart and locked directly into the molecular structure of solid rock.
To really wrap your head around this, we need to take a little journey. We're going down, deep into the Earth's mantle, to a very specific spot that starts about 410 kilometers, or roughly 250 miles, straight down. This is the transition zone.
And this place is exactly what it sounds like. A zone of intense, incredible change. It's like a geological pressure cooker, where the familiar minerals we know from the upper mantle get crushed under unimaginable weight and heat, forcing them to completely transform into new, exotic forms. And this is where our story really gets good.
The conditions down here are just insane. The pressure is around 14 gigapascals. We're talking hundreds of thousands of times the atmospheric pressure you feel right now. And it's hot, over 2,000 degrees Fahrenheit. Now, under that kind of assault, a normal water molecule, H2O, just can't hold itself together. It gets literally torn apart, leaving behind something called a hydroxide ion. That's 1 oxygen and 1 hydrogen atom clinging together. Okay, so you've got all these broken bits of water molecules floating around, but where do they go? Well, they get soaked up. The rock itself starts to behave like a giant, high-pressure mineral sponge.
And this slide right here, this explains the whole magic trick. See, up in the upper mantle, the main mineral is olivine, and frankly, it's terrible at holding water. But as soon as you hit the crazy pressure of the transition zone, that olivine gets crushed and reformed into a new, brilliant blue mineral called ringwoodite. And this transformation is everything because ringwoodite loves water. Its unique crystal structure can absorb up to 2.5% of its own weight in water, a massive, massive jump from what olivine could do.
So let's just break it down. It's a simple 3-step process. First, incredible pressure turns olivine into ringwoodite. Second, ringwoodite's new molecular structure has these perfect little empty spots that are super attractive to hydrogen. And third, those hydroxyl ions, the broken bits of water, snap right into place, locking that water directly into the solid mineral. So it's not wet rock. The water becomes part of the rock.
Northwestern University geophysicist Stephen Jacobson, who's a huge figure in this research, he put it perfectly. He said, the ringwoodite is like a sponge, soaking up water. It's that very special crystal structure that's the whole secret to how you can hide an ocean inside solid rock.
Okay, I know what you're thinking. This sounds like science fiction. How on earth can we possibly know what's happening 400 kilometers underground? Well, it's pretty amazing. Scientists pieced this whole puzzle together from 3 really clever lines of evidence.
So the first big clue came from earthquakes. Using a massive network of 2,000 seismometers, scientists saw that earthquake waves would mysteriously slow down right when they hit that specific depth. That was a huge hint they were moving through rock that was, for lack of a better word, soggy. Next, they recreated the mantle in the lab. Using these incredibly powerful diamond anvils, they proved that this water-bearing ringwoodite would, in fact, sweat a tiny bit of melt under that pressure, which perfectly explained why the seismic waves were slowing down. But the final proof, the smoking gun, was a tiny, ultra-rare diamond from Brazil. It had been forged way down in the transition zone, and when it came to the surface, it had a microscopic piece of ringwoodite trapped inside it. And guess what? That ringwoodite contained 1.5% water. It was the first and only physical sample we've ever had from this hidden reservoir.
All right, so there's a giant sponge-like reservoir of water deep in the mantle. That's cool, but, so what? Why should we care up here on the surface? Well, it turns out this hidden ocean is absolutely crucial for pretty much everything.
I mean, just look at this. This really puts it all into perspective. That first bar? That's all the water in all our oceans combined. The bar right next to it? That's how much water might be locked away in the transition zone. The sheer scale is just mind-boggling, and a reservoir that big has to be playing a vital role in how our planet works.
And it does. This reservoir isn't just sitting there. Think of it like a giant water buffer for the entire planet. It's part of a huge, super slow-motion water cycle that helps regulate how much water is on the surface. It's one of the reasons our sea levels have been remarkably stable over millions of years.
And that brings us to maybe the most stunning takeaway of all, again from Stephen Jacobson. He said, if it wasn't there, it would be on the surface of the Earth, and mountaintops would be the only land poking out. Think about that. Without this deep mineral sponge soaking up all that extra water, our planet would basically be a water world, with almost no dry land at all. You know, discovering this hidden ocean just completely changes how we think about our planet's water cycle and the very forces that make Earth a habitable place to begin with. It really makes you wonder, what other profound, world-shaping secrets are still locked away, just waiting to be discovered, deep beneath our feet?